All right, welcome to the talk, everybody. We're going to be talking a lot about optimization and how we can use GPU acceleration to really take that to new heights. So I'm going to pose a question here for you. What do slime molds, analog computers, and Grace Blackwells have in common? I promise we'll give you an answer to that by the end of the talk, but it should be an interesting journey if you come along with me. So again, I'm Mark Ostroot, the Director of Engineering. Mitch McKay, he's the Engineering Manager. A little bit about Simple Rose. We're doing some pretty interesting novel stuff. We're the first cloud-native solver as a service provider for optimization. So you don't have to own the hardware. We'll solve it in the cloud for you. And we're also the first to harness GPU parallelism for enhanced performance. So utilizing the latest and greatest NVIDIA technology to speed up optimization. And also, it's the first solver that's designed specifically for distributed solutions. So solving across a horizontal scaling structure using Grace Hopper and Grace Blackwell as the engine behind that. So let's talk a little bit about optimization, what it is, and some background and use cases. And so first off, this might be a lot of Greek, and it might scare you a little bit, and that's okay. But under the hood, mathematical optimization is just linear expressions, right? So those linear expressions describe a decision-making process that finds the best possible solution from a set of choices while considering constraints, such as budget, or minimizing or time, or finite resources like a fixed area of a warehouse or something like that. It enables businesses to make better choices to maximize profits, minimize costs, or enhance efficiency. You can use this across a wide variety of different business constraints, so like supply chain, investment portfolio, route optimization, staff scheduling. All those are really hard NP-hard problems, and we use optimization to solve those. So when I say constraint, what do I mean by that? So let's say that you're a manufacturer of forks and knives, and you're trying to optimize the amount of profit that you make. So if you have no constraints, you would just make as many forks and as many knives as possible, and you'd make $900 a day or something, right? But realistically, there's some real-world constraint that happens. So that real-world constraint could be there's a manufacturing machine that you can either use for forks or knives, and that introduces some actual limitation on what you can produce per day. So in this case, as we had one, now the new optimum is 700. But there's inevitably a large amount of these, right? Whether it's I can't get all the resources I want, I have different production constraints to consider, and so we end up designing these polytopes, but describe these strange shapes with all these constraints. And this is a nice two-dimensional case, right, where we can see that plainly here. But these actually go in n dimensions, so they're very hard to visualize, but we're walking along those polytopes as we solve them. So this algorithm that solves these optimization problems is actually the algorithm that runs the world. New Scientist magazine once said that, and there's a huge variety of problems that this is actually engaging with. I promise you've engaged with this on your way to this conference, at this conference, and getting a cup of coffee this morning. So whether it was to figure out which pilot was flying which plane, the prices of the tickets that you paid for to get here if you flew in, whether that was to figure out the prices for retail and figuring out what to charge for any of the NVIDIA items out there, like a hoodie or their nice shirts and stuff. All that took optimization to figure out the demand forecasting and supply chain management to figure out how many shirts they should deliver here. Also, things like healthcare, figuring out which nurses should be on which shift, figuring out which operating room needs to have which patient in it at what time. That also is a very important problem, right? You have all sorts of different considerations there, like how sick a patient is, and also the experiences of the different surgeons or doctors that are helping. And finally, also mineral extraction and natural resource extraction. You've also got to figure out how do we optimize the extraction of natural gas and oil and other minerals what different kind of mining techniques should we employ, or which type of oil extraction method should we use to make sure that we're getting the most amount of good out of the ground for the least amount of energy put in. So really, these optimization use cases are endless, and they have real-world impact. A really good example of this is in fleet management. So FedEx once was quoted to say that if you saved a mile per day per truck, it would save them about $50 million a year. So these have real financial impact for businesses. One of those businesses is the International Ingredient Corporation. So IIC, basically they are a cheese manufacturer. So they have 4 different plants all around the country, and they take in cheese byproducts from 30 different vendors. Now this cheese isn't stuff that you and I would eat. It actually goes to feed pigs, so it's really stinky, gross cheese. But that combination of problems actually is about 4 to the 30th when you have to search through the entire mathematical description. That's about 1 quintillion possible combinations to figure out which cheese should go to which plant. And if you do the naive solution, where the cheese goes to the nearest plant only, you end up having this problem where you get some plants that have a lot of extra cheese, and you have to put that cheese into cold storage, right, into a refrigerator, essentially. And that costs them a couple $1 million a year. And it's very, very expensive. So I wrote this optimization problem to figure out which cheese should be routed to which plant. And that saved them about 6 to 10% freight cost and saved them a couple $1 million a year in terms of overall savings for that company. So now that we know what optimization is a little bit, let's talk about how these problems are solved. So let's start with another small example here. We'll talk about a machine shop. And let's say that you've got about 40 grand, and you're trying to basically figure out which new tools should I put in my machine shop to make the most amount of additional profit per day. So I could either get lathes or presses. If I get a lathe, I'll get $150 per day in output, or if I get a press, I'll get $100. But there's also an additional constraint here we have to think about, which is we only have 200 square feet in our warehouse. So we have to be considerate of that when we're making decisions. So what we do is we describe a simple mathematical model, right? We're trying to maximize our profit per day, and we're trying to keep in mind the amount of cost that we are subject to. So we only have a $40,000 budget, and we only have 200 square feet. But there's a new thing that we have to consider here, which is that X and Y have to be integral, right? We can only have an integral amount of presses or lathes. Half a press isn't going to do anybody any good and won't make any output. So we have to consider that as we're solving this algorithm. So we start that solution by an algorithm called branch and cut. And the first node in branch and cut is called the root node, or integer constraints, and we solve that problem. That produces 2 things for us: this upper bound and lower bound. So in this case, the upper bound's 1,056, and the lower bound is 950. And you can see that once we saw the root node, that X and Y were violating their integer constraints. So X was 2.2, Y was 5.56. So we pick Y, and we divide it into 2 separate halves. So we consider the case where Y is 5 or less, or Y is 6 or greater. And you can see that that produces 2 new nodes, and we have to solve both of those, and those produce new upper and lower bounds. And those will tighten as we keep doing this in the problem. And we're going to keep investigating down node 3, where X is 1.3, and we're going to split up X into 2 segments again. Now you see we have a new outcome in node 5. Node 5 is actually infeasible. It's infeasible because we've gone over budget. If we have 6 lathes and 2 presses, we are way over budget, and that means that we're infeasible. So and because that constraint is violated. In node 4 here, you can see that our upper bound and lower bound are squeezing in again. And Y is also not integer, so we decide to keep investigating Y. And Y, now when we consider Y is greater than 7, again, that's infeasible, less than 6. Now we have a special case here. When Y is less than 6 here, we can see that the upper and lower bound meet. That means that this is actually the optimum solution for this MIP. We still have to search through the rest of the tree because there could be other solutions that are just as good, and maybe there's a business case to figure out whether you'd go with plan A or plan B. But in this case, this is the actual optimum. So, and I'll remind you again that this is kind of a simple, small example, but for the IIC problem, we have 1 quintillion of these nodes to come through. So Rose solves that in under a minute. So how do you search through that space effectively, and how do you make clever mathematical observations to cut down the amount of work is all part of what's key to this algorithm. So let's talk a little bit about the history of optimization and how people have solved this problem before. One of the things we like to do at Simple Rose is get inspired by the past and try to see if we can make old ideas new again. So we'll start off in the 1960s with analog computers. So in the 1960s, NASA was actually trying to figure out rocket trajectories, and they were trying to optimize their pathing to make sure that those rocket trajectories were in an optimal state. And at the time, this is pre-digital computers, they were trying to use analog computers to solve these kinds of problems. Now, I'll remind you, if you haven't seen one, an analog computer is a giant mess of circuitry and wires that essentially was the size of a wall. And they would essentially wire up solutions where they would map the existing linear algebra to actual physical circuitry, so resistances, capacitances, and inductances, and then they would hook that up via plug-in wires in, and it would take months to actually hook up a problem. This is very difficult to debug, and changing anything in the model took a long time because you had to track down which wire it was and make those changes. But the really cool thing here is that it instantly solves linear problems because it uses physics. So under the hood, all of this physics just pops out a voltage, and you can read that voltage and know instantly what the solution is. So the instant problem solving is a really cool feature. Maybe there's a way we can bring that into the future. This is a very cool thing that happened in Japan. So they were using a slime mold to figure out if we can optimize the Japanese rail network. So this is a topographical mapping to a petri dish, where this is the exact topographical map of Tokyo, and they put oats at different city center locations. And those are corresponding to essentially the population density of those areas. And the slime mold grew over 28 hours to figure out an optimal configuration of this network. So we actually see nature solve these problems too. And there's a lot of different use cases where slime molds and other kinds of things in nature solve these kinds of problems. So you can see in the middle here, the slime mold model is pretty different than the actual Tokyo rail map. And they've actually taken some of the outputs from that slime mold model. There's some built-in redundancies that they liked and some more efficient transportation between things. And they've started incorporating that into the actual Tokyo rail map as they've made changes into the future. So this works really well if you can correlate your MIP to a petri dish. Now, for our earlier MIP, where we were talking about presses and lathes, you can't really map that to a petri dish, so we can't really use this solution for that kind of MIP problem. But one of the things that we like about this is that the slime mold is exploring that petri dish in a distributed fashion, right? Each cell is trying to make a good decision as it comes through the search space. So that kind of distributed solution is also something that we really like and we want to keep pushing forward. Now, unfortunately, a lot of companies grow quicker than their decision-making capabilities do. So you end up relying on somebody like Michael Scott here to make good decisions for you. And I don't know about you, but I wouldn't want that. Or you end up with some sort of magical spreadsheet that's linked together and has some sort of equation baked in that somebody did that's sufficiently black magic that if you look at, it's going to break. And so ultimately, a lot of companies find themselves making decisions like this, where they're kind of making a decision on a hope or a prayer or an educated guess. This leaves about 20 to 30% on the table from our expertise, and we can do much better than this. So, also, there are a lot of CPU-based solvers out there. One problem with them is that we're really hitting physical limits of how much we can keep accelerating CPUs as we go forward. And that models have to make sacrifices right now in order to keep solving on CPUs. So modelers will detract from their model to make it less like reality, so we get a less optimal solution, but we'll actually get a solve time on a single CPU. So the only real way to tackle this going forward is to start leveraging parallelism. So rather than using a single CPU, using many CPUs, using GPUs as well to start doing parallel computing there. And if you're not careful about how you do that, you're going to get bottlenecks, right? You're going to do inefficient communication, you're going to move around memory too much, and that's going to affect your overall performance. And so Simple Rose has really tackled this challenge on NVIDIA hardware. We've tried to tackle this with Grace Hopper and Grace Blackwell and designed for that kind of hardware to go forward. So as I was talking about before, there's also limitations to how much we can do a speed up, right? I'm sure you're all familiar with Amdahl's law. If 10% of your algorithm is spent doing a serial operation, then you can only ever achieve a 10x speed up as an upper bound, right? So if you throw an infinite amount of threads of it, you're going to infinitesimally approach that 10x speed up. But in reality, due to communication overhead and memory management and that kind of thing, you actually see most solvers have a detrimental graph like this, where as you add more and more threads, they start colliding with one another. They start doing inefficient memory management. They start having way too much overhead in communication. And so we see a degradation in performance. We don't even achieve the upper bound in industry right now. There's another law called the Gustafsson-Barsis's law. And this law actually stipulates that if you increase the amount of parallel work with your amount of workers, you can actually achieve a linear speedup. And Rose actually is able to achieve a superlinear speedup. So we're able to do this because as we distribute our workload across a distributed solver group, we also eliminate work. So we're not only upping the amount of parallelism because we're searching through that giant branch and bound tree, but as we get good feasible solutions, we're able to prune off work and we eliminate work in the queue. And so that's one of the novel things about Simple Rose. And Mitch is going to talk about the future of optimization and some of our results.
I always try to remember that what he just went over was decades worth of advancements in optimization. And it's typically a topic that only people with an advanced degree actually know about. So if this is all new to you, it shouldn't be a surprise. We're going to talk about the future, and we consider it quite rosy. So Rose is our underlying solver. It is a distributed solver. It is the first GPU-enabled MIP solver, and as Mark had mentioned multiple times before, we've seen superlinear speed up. What do I mean by that? If you add a few more machines, you'll see a speed up greater than the amount of machines you've added. And that is tied to how we're actually addressing the tree. It allows us to learn more about it early on and make better decisions. Next, we're going to talk about NVIDIA's cuOpt. This is a GPU-powered solver, and I learned that recently. For a while, I've been saying it's a heuristic solver, but it actually has a lot more tricks underneath its hood now. And there's a talk that we're going to show later on that actually goes over all the things that cuOpt has, and as everyone is probably aware, it's been announced that it's going to be open sourced. It scales seamlessly, and this is targeted at giving real-time solutions. You don't always have 5 days to run your problem and hit a solution. Sometimes you need something today to take an action. And so we decided that if cuOpt is working on this, and we've been working on this, scaling, solving larger problems, giving quicker solutions, we should work with them. So, taking cuOpt that gives you very fast feasible solutions that allows you to take action in the moment, and Rose, which is built to give you optimal solutions, which provides additional savings, and those savings are tied to the business at hand. You know, if you're a large multi-trillion-dollar business, you may save a little more than the local distillery. I'm also going to add something. If you're not aware, last week, a lot of tornadoes went through the US. And it was something like more than 100 tornadoes across 72 hours. So why does this matter? Well, if tornadoes go through and airlines get blocked because planes can't fly, houses get torn down, power lines get torn down, you can't rely on something that you ran a month ago that didn't account for this. This happened very recently. You immediately have to go through and figure out how to dispatch people, how to get power back on, how to get people flying to their destination on planes. All this needs real-time action. You cannot wait. And that's what we're really trying to target. And I thought it was interesting that this just so happened right as we came out here to talk about it. So how do we actually stitch these together? If you recall, Mark had a tree very similar to this. Up at the very top, we have a root solve, where we ignore the integer constraints and we solve the LP. And this is a race. We hand off the problem to cuOpt, and then Rose will take the problem, and we race. And what we want to do is see who's going to win. After the first solver finishes, we're going to do some updates to the model, and we keep resolving, and there's a lot of tricks that we have at the root. But as soon as we're happy with the root solve, we launch what we call branch and cut. And this has a lot of tricks underneath it. But while we're doing branch and cut, Rose will reach out to cuOpt, and we're sending over HTTP right now some information about the model. And what's interesting is, in our testing, we were expecting very similar results to QOpt, but we found that our model updates actually made QOpt more effective. It gave them better solutions. And throughout the solve, throughout the MIP solve, these two systems will communicate back and forth, and they'll eventually hit the optimal solution. And this is generally considered the end goal, but sometimes, as I said before, if you have a disaster, you need real-time solutions. You cannot wait, you cannot look for optimality, you need something to act on today because power lines are down, planes can't fly. Think about an ice storm. Sometimes that takes out the power, and if you don't have heating, you can get in a lot of trouble. So now that we've covered what we consider the future of optimization, we're going to talk a little bit about the numerical results that we saw with QOpt. So here, this is that root problem, the top of that tree, that very first node. And we saw up to a 50x speed up. And to give you a little explanation on how to read this chart, the red bars represent how much speed up there is. So the big one on the bottom is that 50x speed up. Up on the top left, you'll see a 1x speed up. And that's us trying to highlight if QOpt doesn't participate in the root contest, or if ROSE happens to be the first to solve, it doesn't impact our solve. They can only help. We're cooperating together to get a better solution quicker. On the very far left are the list of problems, and we see an average of about 7.12x speed up across our root solves. I'll also add that we do have the ability to run this at each node if we choose to. Generally, the root is a special case in a MIP. Next, this is across the full MIP solve. So if you recall those trees, this is traversing that entire tree until you get to the solution, the 4 to the 30 nodes or possibilities, if you have to brute force it. And in this case, again, up in the top left, we have 1x because QOpt cooperates with ROSE and it can enhance its effectiveness in solving MIPS. But if it doesn't actually participate in the solve, ROSE will still solve just fine. And we saw up to 61.7x speed up. And the problems are on the left again, and the red bar correlates to the speed up. And that's about 6.06x speed up on average across this set. Now, these are just general results. They're really interesting, but we really like to look at problems. If you were actually on the development team, you would be looking at individual problems because not all problems behave well. So first we're going to look at a problem that ROSE did very well on, and I'm going to give a little bit of an explanation on how to read these. So at the top at the title, you'll see the problem in parentheses on the right, and you'll see a dash, and it'll either be baseline or QOpt. QOpt tells you if QOpt was running inside of ROSE or alongside ROSE. And if it says baseline, it's just ROSE on its own. And when we did this, we're trying to isolate what the effect that QOpt has. So this is a single Grace Hopper system. The top line, you have this dotted line, that's what we, little jargon, there's primal bound, dual bound, there's upper bound, lower bound, and feasible bound, integer bound. I'm going to say upper and lower so that no matter what level of knowledge you have, you understand upper's top, lower's bottom. But the upper bound is integer solutions. The lower bound is those infeasible solutions, those nodes that we're going through, and what we're really trying to do is pinch them together, because if we pinch them together within a tolerance, we've proven that we've hit the optimality to whatever the user specified. If they want optimality within 10%, you can cut that off at 10%. If they want optimality within 10 to the negative fourth, we can do that. So in this case, ROSE takes those two bounds. We get a lot of updates very consistently, and it solves it fairly quickly. In the next case, this is the nurse schedule sprint 02. It's the baseline, so QOpt's not participating. And again, this is a single Grace Hopper system. Recall, we are aimed at a distributed solve, but we're really trying to isolate what we can do with QOpt. And we, over the course of an hour's solve, have a small gap, 57.5 to 58. So it's not massive. We have some pretty decent updates, but we didn't quite close that gap. Well, when we ran it with QOpt gave us some really early solutions. ROSE is able to take those solutions, make certain decisions about the tree, and close the gap much quicker and solve it in half the time. A more interesting case is a problem like this, where ROSE does have some updates, but it's not making nearly as much progress as we'd like to see. And so in this case, distributing it, we see a lot better results, but running in this single case, we were hoping for a little more gap closure. But when we ran it with cuOpt gave us some really good early solutions, and Rose is able to take that and drive it to optimality much quicker. And again, I'll highlight that if you happen to use cuOpt and those green bars are your solution, well, they may not be, right? Recall, we actually increase the effectiveness of cuOpt. With some of our pre-processing, we're gonna actually add some additional constraints that will help cuOpt get better solutions. But if you happen to be using cuOpt and you're waiting about 1,250 seconds, you'll notice that Rose almost immediately gives it a massive update. So together, these two solvers are really working to give users fast, feasible solutions that allow them to take action in a reasonable amount of time. So we had this question at the beginning. What does slime mold, analog computers, and Blackwells have in common? Hopefully you came to optimization. Maybe you also thought of cuOpt and Rose. For us, we really see cuOpt as being very similar to that analog computer. You stitch together this big system, and it gives you a nearly instantaneous solution. cuOpt is very similar to that, except, well, NVIDIA did the computer stitching for you on your behalf, right? So you just have to go buy a GPU, or we are a SaaS platform, so you can, from your cell phone, execute a solve. And cuOpt is just an advancement from these analog computers. And slime molds are very similar to Rose. It's a series of individual entities collaboratively working on a problem. And together they can actually get a better solution faster than you would if it were just a single entity. So we'd like to go back to that initial IIC problem, 4 to the 30 possibilities. If you assume some simple operation, something like incrementing an integer value on a modern CPU, you don't have to understand how that works, but we went ahead and ran the math. If you brute forced it, it's about 288 million seconds. Well, Rose solves it in under a second. Actually, I spend more time trying to upload the problem on the website than it takes Rose to solve it. So we'd like to encourage people to not try to tackle these problems and to reach out to people who actually are very specific and they focus on trying to solve these problems on their behalf. I'll again highlight that if you enjoyed this, we have a QR code for you to scan that will take you to Simpro/GTC. The slide deck is posted there. I really hate having to try to go from photos, so it's nice when people supply PDF slide decks. Additionally, you'll be able to go to our dev blog, and there was actually just this morning another post from the group that stood up cuOpt and Rose on a cloud platform, and they have a little blog on how they did that. So if you happen to be looking into those sorts of things, it might be interesting. We do have a consulting group that will help people if they've never actually dealt with optimization. They'll get them along, and feel free to reach out. Finally, I'd like to call it a few talks. Yesterday, there was the first talk up there, the supply chain analytics, had one of the best explanations of optimization that I've ever heard. Additionally, there was the advances on decision optimization, which had some phenomenal details on how cuOpt actually works, and not just that, how MIPS work. A lot of us take different methods for explaining things, and sometimes having more than one explanation helps. And then later on today, there is actually a workshop on accelerating portfolio optimization. And I'd invite people to go see that as well. Mark, if you'd like to come up, I think we're ready to start taking questions.
Go back a slide.
We'll open up for Q&A.
Hey, thank you. Good morning. In the beginning of the session, you mentioned the benefit being your architecture minimizes the amount of memory movement. And then we talked about the slime molds. And I think I got confused are you using that methodology to architect the distribution and reduce your memory transfer footprint, or another means?
Sure, I can take a stab at answering that. Yeah, so the slime mold, we were really just trying to be inspired by what's out there in nature and see what we can do differently today to try to advance the field. Really, there hasn't been wide adoption of distributed computing in solving MIPS, and when there has been some tests in that, the performance gain has been subpar, essentially. So we've tried to build our solver from the ground up, being very conscious of memory movement. So we try to minimize the amount of memory movement, and we're very aware of what kind of asynchronous communication we're doing. So that allows us to achieve a much better speed up by doing distributed computing compared to other solvers.
Thank you for the presentation. Pardon my ignorance, but two slides that you showed, the bar charts where you achieved like almost 6%, 7x speed up. Are those like some benchmark problems that you ran the?
Yeah. So there's a common data set called MIPLib. There's a collection set of about 680 problems, and those are like well understood MIPS. They're used a lot for benchmarking and for testing and those kind of things. So those problems all come from that public data. So you yourself can go to MIPLib and go download them and look at them if you'd like, but they're publicly available.
Any other questions?
I guess going back to the question on your when you submit your job, other than defining your problem, what variety of, I guess, runtime parameters are available through your cloud system? For the problem it's specific?
So you can vary the amount of distributed compute that you want to submit, essentially. So more compute means more leveraging, faster solve times for your problem. Not every problem is going to need all that horizontal compute. So there's a wide variety of parameters too. There's many different techniques that you can use to turn on or off and that kind of stuff. Many different solvers have all sorts of things like enabling certain types of cuts or certain types of pre-processing. So we match those kinds of parameters as well. It's really just following industry standards. So.
Earlier you mentioned executing both cuOpt and simple rows at the same time in some kind of flowchart. That reminds me of, and I believe it's common to do both primal and dual simplex at the same time because you don't know which one's going to solve faster. And I think in those cases that's helpful because you can get more parallel work, and we have so many threads on CPUs these days. Yeah, it's this one that there's no cost to it. But in this case, do your workloads basically, if you just do rows to start with, does that fully saturate the GPU, or does solving with cuOpt as well essentially allow you to fully utilize the GPU better?
Yeah, so pre us working with cuOpt, we were marshaling all of the resources on the CPU and GPU. So to run cuOpt, we take a couple of our nodes and sacrifice the GPU and basically let cuOpt run on it. It doesn't use all of the resources on the GPU it depends on problem size. So we can also run stuff on it. Right now, we're letting cuOpt kind of have its own GPU and then using the rest of the hardware in the distributed solution for ourselves. So
I'll add that similar to your comment in terms of running primal and dual simplex together, we just put a little box for Rose's root LP solve. It's actually a lot of techniques and variations of those techniques running. And it's a very common practice to do that at the root because you don't always know what will be the best way to solve the LP until you actually see it come back with a solution.
Any other questions?
yeah, one more.
All right, this is a little maybe off topic, but related.
Sure.
Is a lot of times in practice, maybe you have a computational method that you want to evaluate at each node that is a longer runtime. And traditionally with these solvers there's no way to plug in sort of an external calculation that'll run within your methodology. Have you encountered that? Or a good example is in robotic programming. Say you solve a task sequencing problem over your robots, but then you have geometric motion planning aspect that informs or adds additional richness to those solutions,
Yeah.
but you can't run those in parallel. It's like you have to constantly go back and forth.
Yeah. So this might. I'm not sure I'm understanding the question, but I'll take a stab at it. So essentially, one of the ways that we're utilizing cuOpt is it's running in parallel. So if you run cuOpt itself, it would give you kind of those heuristic solutions back. And we're trying to use that to inform our currently running algorithm. There are other methods that we're communicating with too that are basically all competing to provide best solutions. Some of them, most of them, we've wrote cuOpt's the only external one that we're using right now. But there are also scenarios where people will want to do like what-if analysis, where you have, let's say you have logistics and you're trying to figure out, okay, what if there's a strike here? What if these shipments get delayed, et cetera? And so you look at a wide variety of the same problem with a wide variety of different kind of use cases. Sometimes you can take solutions from one of those and use it as a starting point in a different use case, and it lets you kind of start later on in the tree. It's not necessarily going to be the same optimum, but it helps you eliminate work. So in those kind of what-if scenarios, we can do that to help start. It's called warm starting, and so we do that as well for those kinds of things. Yeah. No, absolutely. I'm happy to talk to you after too.
Is it deterministic? Do you have a seed if you want to drive it? You want to rerun from scratch, but you want to drive it to the same solution. And second question was, can you save your context? So say like I didn't, say I ran to optimality, saved that context, ran it on, tested the solution for an enriched solution, found out it was infeasible on the other constraints, and then hit that context again to find me, okay, that was infeasible, find me the next best optimal.
Yeah, so when you feed in that warm start, it gives us that same starting point, and then we'll use that as a initial condition and keep pushing forward from there. But actually, on the determinism front, that's actually one of the things that we try not to do, is to try to not be deterministic, because that puts a barrier on distributed and parallel computing. And that actually causes quite a slowdown on performance. So by not being deterministic, it allows us to efficiently use distributed computing more effectively. That's why we're able to achieve super linear speed up.